So I welcome everyone to this course on aerodynamics, right? And you may study various courses in the aerospace engineering. Probably we can say that aerodynamics, aircraft structures, propulsion, and then you will move to computational fluid dynamics, avionics, and so on. But for any aerospace engineers, the aerodynamics is one of the strong basic subject, because whenever we start designing something, right, designing an airplane or designing an airfoil, designing an wing, um, we just start with the aerodynamics. The aerodynamic shape, it matters for any such design, right? So there are something we need to follow in this class, right? So how to be happy in aerodynamics course. So I recommend you to try to attend all the classes, right? It is in Google Meet, and from your home you can attend comfortably. And if you have any question, you can write in the Google Classroom, or you can write an email to me, or you can call me, right? So try to attend all the classes, take notes on the classes, right? I recommend you to maintain a notebook for this subject, because we will be deriving most of the equations. So it is necessary to take notes in this class, right? You should maintain a notebook, right? And also, I recommend you to read at least 20 minutes a day. That is what the preference, right? You can give 20 minutes a day to read what we are discussing, right? I will tell you the textbook for this aerodynamics course, and I follow that John D. Anderson's aerodynamics book, and I recommend you to have one book on aerodynamics, right? There are many books available. So in general, I can ask you to have at least 2 books, because these books will be really useful even when you prepare for GATE examination, or something like scientist entrance test, or ISRO entrance, and whatever you want. So I recommend you to maintain these points, right? So 2 books, then do the assignments and the cycle test properly, so that you can score, right? So enjoy learning aerodynamics. It's an interesting course, right? I recommend you to start from the first day, and if you have any question, please ask me. So we follow John D. Anderson's Fundamentals of Aerodynamics. There are some editions, but 6th edition is good. So I recommend you to have this book. The book costs around 500-600 rupees probably, and it is available online. I recommend you to have one textbook. It's like a low price edition only, right? Then Katie Foundation of Aerodynamics, Cowton Carpenter, Cowton Carather, McCormick, Bertin, all these books are available. If you want to refer, you can do that. You can have these books, or you can borrow from the library later, and you can just go through. But I recommend you to have John D. Anderson's Fundamentals of Aerodynamics book, so that you can follow the class nicely, right? Then why we always recommend Fundamentals of Aerodynamics by John D. Anderson? Because this is one of the wonderful book to learn aerodynamics. It's almost like a storybook. Probably you might have studied that Introduction to Flight by John D. Anderson, right? Is you have studied, Karun?
Yes, sir.
Yeah. So you have the book on Introduction to Flight by John D. Anderson, right?
Yes, sir. Yes, sir. I have, sir.
Yeah. Good. Thank you. So we follow this John D. Anderson for these aerodynamics related courses. Say this is John D. Anderson. He is from National Air and Space Museum, and then Smithsonian Institute, and then he's emeritus professor from University of Maryland. The point here is we always follow John D. Anderson book. So Introduction to Flight, if you have gone through Anderson's language, then the fundamentals of aerodynamics also looks similar, right? So we have a point that in the third semester you follow Anderson's Introduction to Flight. Fourth semester you follow Fundamentals of Aerodynamics by John D. Anderson. Then fifth semester you follow Modern Compressible Flow by John D. Anderson. And again, sixth semester you will follow the Aircraft Performance by John D. Anderson. And again, Computational Fluid Dynamics. Then seventh semester you will follow Hypersonic and High Temperature Gas Dynamics by John D. Anderson. Right? So we follow Anderson in the aerodynamics related courses. So I recommend you to start reading the book, right? And then you will be used to the John D. Anderson's language, right? Well, let us start the discussion on aerodynamics, right? So in brief, the term aerodynamics is generally used for the problems arising from the flight and other topics which involves the flow of air, right? When there is a dynamics of air, then aerodynamics is involved, right? Ludwig Prandtl, who is called as the father of fluid mechanics, so he gave this definition, right? Then in the dictionary, American Heritage Dictionary, we can see that the dynamics of gases, especially atmospheric interactions with any moving object, we can consider the aerodynamics, right? So when there is a movement of any body in air, the body experiences certain force, the body experiences certain moment because of the the relation between the flow, pressure, density, velocity, and all those things. So we discuss about these fundamental parameters in aerodynamics, right? Okay, so why we need to learn aerodynamics, right? So starting from 1930s, the Douglas DC-3, the aircraft is one of the low subsonic transport aircraft designed, and without the knowledge of aerodynamics, they could not have this kind of aircraft, right? So starting from 1930s, right, there is a very nice subsonic transport aircraft, and that was designed with the knowledge of aerodynamics. Then later, so this aircraft is a very low speed subsonic aircraft. However, the next one is Boeing 707. It's a high speed subsonic, still subsonic, but it's a high speed aircraft, right? It has created a high speed flight in late 1950s, right? Then see, in this development from the subsonic to high speed subsonic, we have a further flight, right? So it is a supersonic flight. So it flies faster than the speed of sound, and it is like Bell X-1 in 1947. Then further, right, the further supersonic flights which can fly 2 times that the speed of sound, that is Mach number 2 we say, right? So Lockheed F-104, it was there in 1950s. Then Lockheed Martin F-22 is a sustained supersonic flight, right? And it is used for used as a fighter aircraft, right? So with all these aircrafts, if you see from the subsonic, high-speed subsonic, transonic, supersonic, and now even hypersonic flights are existing. All this is because of the basic aerodynamics, right? Now, this is an interesting aircraft. This is a blended wing body aircraft, right? The body shape itself, looking very much different. And this aircraft has almost 300 to 600 passengers it can carry. and the fuel efficiency is really very good. They claim that with the 30% of the fuel when compared to the previous version of the aircraft, this aircraft can perform, the aircraft performance and the efficiency is very good. So you see the difference in all these, right? From the low speed aerodynamics, high subsonic speed, right? This is subsonic speed and high speed subsonic flight, supersonic flight. This flight maybe it crosses the barrier, sound barrier, right? And then two times that of the speed of sound, and now sustained supersonic flight, and now the blended wing body configuration. So by all these means, we can say that the design, the aerodynamic design of the flying vehicles are really important, right? So we need to study about aerodynamics. Maybe we can modify the aircraft or we can modify the airplane wing in such a way that it can produce much better aerodynamic efficiency, right? Okay, so why we learn about aerodynamics? Is it aerodynamics or say we can say that the aerodynamics is only for the airplanes, right? Whether the application of aerodynamics is only for the aircrafts or launch vehicles or supersonic aircrafts, is it only in the aerospace domain?
No, sir.
No, because I told you when there is an interaction between the solid body and the air, then the aerodynamics comes into existence, right? Now you may be sitting in your home and you might have switched on the air conditioning system or you may be exposed to the fan. The aerodynamics is involved, right? So when you open your window, the aerodynamics is involved, right? Even though in our Indian atmosphere we don't design a house with aerodynamic knowledge, but the ventilation it matters, right? So every time the comfortability of the persons inside the room requires aerodynamic knowledge. So by all means, the aerodynamics has lot of application throughout the various engineering field. So let us say some examples. So we can say that the airflow over the automotive vehicle, right? So we can say that in the automotive vehicle, right? So automotive vehicle, you might have seen the automotive vehicles, right? So from long back, the vehicle was so blunt and now it is nicely shaped, right? The aerodynamic shape and the change in aerodynamic shape is inevitable, and every time when they change the shape, they prove that there is a improvement in aerodynamic efficiency as well as the fuel efficiency of the automotive vehicle, right? Then the gas flow through the internal combustion engine, right? So here the gas flow through the internal combustion engine, and then the weather, say presently we can say that you might have seen in the the weather prediction system, they say that the low pressure region is created at some location in the Pacific Ocean, Indian Ocean, and something like that. So the change in pressure which creates the movement of air, and there also the aerodynamics is involved. Now the prediction of the storm, right, also have an aerodynamic influence. The flow through the windmill, you might have seen a very big wind turbines, right? The wind turbines, now the wind turbines, the rotor diameter may be of 200 meter, right? You can imagine the 200 meter, right? So such a big structure, the aerodynamics is very important in order to have a better efficiency, better energy efficiency also, right? And the production of thrust by gas turbine engine, and then the rocket engines, not only the rocket engines but also the outer surface of the rocket design. Aerodynamics is involved. Right? Again, the movement of air through the building heater, air conditioning system, wherever you say there is some flow of air, then the aerodynamics is involved, right? And hence we can say that aerodynamics is not specific to aerospace engineering, right? So we can have the knowledge of aerodynamics as an engineering course, and we can apply it wherever we want. Well, we will have some of the basics, right? So the basics from solids, liquids, and gases, right? Okay, before going to that, I want to ask you if you have any question or anything, please let me know. If there is a question, I will try to answer. Okay, then we can have the discussion at the end of the class, right? So we start with the distinction between the solids, liquids, and the gases, right? So the basic difference is you put a solid in a large container, I mean, inside a closed container, whatever it is, there will be no change, right? There will be no change in its shape or its boundary. So both remain same. Now, what you can do is now you put a liquid, right? When you put a liquid into a container, what happens? The liquid will change its shape, and in order to confirm the shape of the container, right? And the boundary of the liquid will be same as the boundary of the container, right? Now, if you put a gas inside the container, what happens? The gas will completely fill the container, right? The gas will completely fill the container and taking on the same boundaries of the container, right? So the word fluid is used to denote either the liquid or gases. The more technical discussion between the solid and fluid, say usually we ask the question, what is a fluid? So many discusses about the fluid and they say simply something which flows is a fluid, but it is not the definition. So the main technical discussion is, say when you consider a particular state, right, say a solid, then you apply a force tangentially, right? So how we can apply a force tangentially? Say if this is a solid object and if you apply a force tangentially on its surface, right? So when you apply a force tangentially on its surface, the solid will experience a finite deformation, right? So how that finite deformation looks like? Probably the solid may change its shape like this, right? And then we can say that this is a tangential force per unit area, and we can call that as shear stress, right? So usually the shear stress is proportional to the amount of deformation, right? Again, in the other case, like when you apply a tangential shear stress on the surface of the fluid will experience a continuously increasing deformation, right? So, and the shear stress is usually, it will be proportional to the rate of change of deformation, right? So here, if you see, there is a amount of deformation. Here, rate of change of deformation we have. So in the basic fluid mechanics, you might have studied that the shear stress is directly proportional to the rate of shear strain, right? So that is the basic point we want to consider in a fluid, right? Then the most fundamental distinction between the solids, liquids, and gases in the atomic and molecular level. Say if you consider a solid, the molecules are very much closely packed, right? And we say that their nuclei and electrons form a rigid geometry structure, and it is almost like a glued intermolecular forces, right? But in the case of liquid, there is a spacing between the molecules, and that is significant, right? And the intermolecular forces are still strong, and they allow enough movement of molecules to give the liquid the fluidity, right? So that is what creates the fluid to flow. Now, in the gas, the spacing between the molecules is very much larger, right? Say very much larger. Say we can say in this way, in a standard condition, the space between the molecules is some 10 times more than the molecular diameter, right? So we can imagine that the gases, the spacing between the molecules are very much significant, right? So the influence of intermolecular forces becomes weaker, and the motion of the molecules occurs freely throughout the gas. So this movement of molecules in both liquids and gases leads to a similar physical characteristics, and hence we put both gas and liquids under a single title called fluids, right? So it is very much different from the solid, right? So this is the basic difference we can say, and this is also justifying the gases and the liquids to be a fluid. So therefore it makes sense to classify the study of dynamics of both liquids and gases under the same title, fluid dynamics. Even there are some differences. Even if you consider the different gases, the characteristics are different, but it is fine, right? Still, it can be considered as the fluid dynamics. So therefore, the fluid dynamics, we divide that into three different areas. One is hydrodynamics. For example, you might have studied the fluid mechanics in the last semester, where in most of the cases you might have considered the liquids, right? Second one, gas dynamics is flow of gases, and aerodynamics is flow of air, right? Now, now we will go a little deeper into the aerodynamics, what it is. So aerodynamics is an applied science with many practical applications in engineering, right? And you may talk about the aerodynamic theory, thin airfoil theory, surface integration of pressure, and then you may say that lattice method, Kutta-Joski theorem, sink, doublet, whatever you can say, and you can derive whatever the mathematical equation, right? And end of all the discussion, we arrive to a particular point, right? Practically, we call this as to predict the external flow, and again to predict the internal flow. So this is actually called as external aerodynamics, and this is an internal aerodynamics. Can someone say an example for external aerodynamics?
Flow over airfoil.
Flow over airfoil, then Charan Dej. Charan is there? Charan? Okay, Aparna Mahadevan.
Yes, sir. We try to mitigate the heat during relanding, sir. Reheat management, sir.
Okay, through the air, right?
Yes, sir.
Yeah, dissipation of heat through the air.
Through the air.
Yeah. Okay, then Hari Balaji.
Yes, sir. Airflow through jet engine.
Air flow inside the jet engine is an example for internal aerodynamics. Nice. Then Janani.
Yes, sir.
Yeah. Can you say any one example for external or internal aerodynamics? Karthik.
So, airflow around this gas turbine, that is no wind turbine, sorry.
Wind turbine. Yeah. Good.
That's external flow.
Okay. External flow. Good. Mugil.
Sir, shock waves on the nose of the rocket.
What is that?
Shock waves on the nose of a rocket.
Ah, okay. Design of the nose of the rocket engine, right? Rocket.
Yes, sir.
Good. Rohit. Rohint. Both are there. Yeah. Rohit, tell me.
Airflow over a car moving car.
Hmm?
Airflow over a car moving car.
No, I couldn't hear. Could you please loud? Any answer is fine. Don't worry about the answers. You are allowed to say wrong answers.
Sir, airflow over moving cars.
Ah, moving cars. Wonderful. Anirudh. Anirudh Ranganathan. How about Bashit? Bashit Tujain. Flow inside the aircraft engine. Good. Bashit.
Airflow inside compressor.
Compressors. Okay. Okay, good. So, thank you. Now, we understand that whatever we study, finally we arrive to two main points, right? One is to understand the external aerodynamics, and the second is to study the internal aerodynamics. That's all. So, no matter you talk about the theory, complex mathematical equations, derivations, right? So, practically, this is our ultimate goal, right? And we will see how we work on that, right? So, the prediction of forces and moments on and heat transfer to the bodies, right? Usually, this moving through the air, we can study external aerodynamics. Say, for example, if we are concerned about the generation of lift, drag, moments, right, on airfoils, fuselages, engine nacelles, even for the whole airplane configuration, right? So it is important to have the knowledge on aerodynamics, right? Again, if you want to estimate the wind forces on buildings, ships, and any surface vehicles, automotive vehicles, you need to know aerodynamics, right? Hydrodynamics on surface ships, submarines, torpedoes, all require the knowledge of the fluid flow. That is external, even we can say aerodynamics or hydrodynamics in the different cases. So we need to calculate all the required characteristics based on the external flow is for the external aerodynamics. Then the internal aerodynamics, right? Flow inside the duct, calculate and measure the flow properties inside the rocket engine and the jet engine, air breathing jet engine. Even when some aircraft have a propeller engine, so we need to understand how the flows are there in the propellers, whether we can change the design of the propeller and so on, right? So we need to have the knowledge of aerodynamics to predict the flow, internal flow and the external flow, right? Usually the external flows, internal flows, we use wind tunnel, right? So we have a wind tunnel in our university, and I don't know whether you have the information that we have a supersonic wind tunnel with Mach number 3.5, up to 3.5 we can go, and a subsonic wind tunnel of 60 meter per second maximum, and another subsonic wind tunnel having a test section of 1 meter by 1 meter with a maximum of 28 meter per second. And we have another axial wind blower with a test section of 1 feet diameter, right? So basically now we have 4 wind tunnels established in our university, right? And we use all those wind tunnels to study the aerodynamics of various vehicles, right? Okay, so external aerodynamics we concentrate mostly. Okay. Okay, let us start with the fundamental aerodynamic variables. I want to start from the fundamental aerodynamic variables and the flow fundamentals from the uniform flow, source flow, sink flow, and all those things. So I recommend, even if you have already enough knowledge on that particular topic, but still please look into that. And I will be using the terms used by John T. Anderson, and hence it will be easy for you to prepare. So let us say the fundamental aerodynamic variables are like pressure, right? Say pressure, density, temperature, and flow velocity. So assume here this is an airfoil, right? And there is a flow, right? There is a fluid flow. And please consider one small fluid element. We can say the fluid element can be infinitesimally small, right? But what we do is like we zoom it and see, okay, this is a fluid element, right? In certain cases, we can say that this fluid element is a volume, right? Volume of a fluid element, elemental volume, right? Okay. So now we will define. What is pressure? Is a normal force applied per unit area exerted on the surface due to the time rate of change of momentum of the gas molecules impacting on that particular surface. So let us say dA is a elemental area at B, right? What is B? B is a fluid element, right? And we have the elemental area dA, and dF is the force on one side of dA due to the pressure. So we can say that pressure at point P in the fluid is defined as P is equal to dF by dA, right? With a limit we say in order to explain it as a point property, right? So force per unit area is a general information. Now, the second one is density, right? What is density? Here we consider dV is a elemental volume. I told you the B is a small, infinitesimally small element, and we consider the infinitesimally small fluid element, right? Have a volume of dV and has a mass of the fluid inside dV is dm. So the mass by volume, if you want to have it at a point, then we can say that dV tends to 0. In all these cases, even we consider a limit of the dV tends to 0, but it doesn't mean that it is exactly 0. It may be considered as very small, that is infinitesimally small, right? So we can write here the density is mass to the volume, right? Elemental volume dV and mass is dm. Temperature takes an important role, especially in the high-speed aerodynamics. Um, Maybe in the low-speed aerodynamics, we may not have such a discussion because when you move to the compressible flow or further, you will have the temperature involved, right? So temperature T of a gas is directly proportional to the average kinetic energy of the molecules, right? And we will have a further discussion on temperature later, right? Then the flow velocity, right? Flow velocity, the definition here, we can say that the velocity of the flowing gas at any point B in the space is the velocity of the infinitesimally small fluid element which sweeps through B, right? So the flow velocity has both magnitude and direction, right? And hence it is a vector quantity. We write in further, so V is equal to U I plus Vj plus Wk. So we mention this flow velocity V, right, in a vector quantity. Again, in contrast to the pressure, density, and temperature, all are scalar quantity, but here we consider the velocity, which is a vector quantity, right? So this is the fundamental aerodynamic variables, and with these fundamental variables, we will proceed further. So we will have the discussion on the shear stress, pressure, and all those things, right? So say for example, aerodynamic forces and moments, that we will have a discussion in the next class, right? Thank you very much.